thank Professor Lee for the excellent talk. And actually, we inspired by Professor Lee's work a lot, and we are currently following Professor Lee's work. The collaboration under the similar environments. So today, my talk is about the toward immersive and natural interactions in large-scale virtual environments. And firstly, I will show a demo. So this is actually the Apple Vision Pro. It just released several days ago, and it's the spatial computing technique enables the device to seamlessly integrate the virtual contents into the environment. And by using the sort of sensors and cameras, the Apple Vision Pro can create the surrounding space and position virtual elements in real time, creating more immersive and interactive experience for the users. So this demo is very cool, and the totally immersive VR scenes and also the augmented scenes can be displayed, and the user can interact with the other people with very high quality. Okay, so um, okay, so in virtual reality, there are three eye characteristics: the immersion.
Excuse me, we can't hear you.
Hi, Professor Pan. Can you hear Professor Wang's talking?
No, I cannot. I just text messaged him.
Okay. Let's wait for him for a while.
Yeah. I think he's restarting. Okay, cool. We can see the screen, but no voice at the moment.
How about now? Can you hear me? Hello? Hello?
Hello, we can hear you, but we cannot see your screen. We cannot see your
So I will
slides.
I will share my. Okay, can you see the screen?
Yes, but no slides yet.
Okay.
Okay, good.
Sorry for the network issue. So I go faster. So these are the characteristics of VR. And do you expect immersive and natural interactions in very large scale virtual environments? So this is an example. This is an ideal example. The user is playing the VR game, during the large-scale virtual environments, and he's also in a very large, very big, the physical space as an underground area. This is an ideal scenario that the user can have a very big physical space. And in our daily life, users, we use devices in our office, in the living room, so we don't have so big physical space. This is actually what it looks like in our daily life if you play VR game. So we are in a very relatively small physical environment, and the machine can be very large. And the physical space limits the large scale workers. So if the user walk along his way, there can be some collision between the user and the wall or the obstacle. And this can be very dangerous. And the user may hit himself to hurt himself. So challenges we are facing are twofold. First, the limited physical space hinders the user movement. The second is the similar spaces can push on the user's collaboration, and this issue is addressed very well by Professor Lee. And we have proposed solutions to this problem. Firstly, the perception we have to use radioactive level, and we measure the perceptual gains and the potentials for the research. And at the level, we have to align the virtual and the physical environments that you're working with. And at the level, we have released the open source library and benchmark for the redirected working technique. And fourthly, we have proposed a concept to use the proceeds for the distributed virtual environments. And these papers have been published in VR, ISMA, and TVCG. So I will go to the first work. So the problem is how to move in virtual space when the physical space is limited. So in this page, you can see on the left-hand side, there is a relatively large physical space, and it's relatively empty. But the user can maybe he wants to experience much larger open scene. So techniques for locomotion, the common ones. First is teleportation. The user can throw a parabola to specify the target position that the user wants to go, and the teleportation technique can be used to position him to that place. And the second one is the walking in place technique. The user can walk in place on a treadmill, and the mechanical device can help him to walk through it. And the third technique is called redirected walking that we use to make the user experience the virtual environment. So with redirected walking, the user can walk in a straight line in the virtual space, but we can redirect him to walk along a curved line in the physical space. So here is an example of the redirected walking, and also short as RDW. So the left-hand side, the user walk along a curved line, and he is redirected by changing his viewpoint very slightly during walking, but he cannot perceive that, and he walked in the tree, but still along the straight line. And the idea to match the passes between virtual scene and real scene. So in the large virtual space, the walking path is straight, and in this optical space, the walking path is curved. So the key is to compute mapping between the sample points along the lines. And we try to do mapping by manipulating the viewpoints of the user during work. So we use games to manipulate the taxes. So we control the user viewpoint to stay away from physical space boundaries. There are typically three types of gains: the rotation gain, the translation gain, and the curvature gain. Each gain should be limited within a range, which is called the imperceptible range. Also, the upper and the lower bound of it is called detection threshold of the gains. So, for example, the detection threshold of the rotation gain should be the 0.67 to 1.4. These gains are measured by the user experiments and can be used to manipulate. For example, if they use 1.5 and the user walk in the physical space strictly in and then the people walk in the space at 1.5 meters. Structures are estimated by user studies, uh, and and I in the application and in this in the user studies, users walk along along the along the way to create as you can see on the left side. And the procedure is called the two orders. First, two FC. The I follow currently there was there taking the two position option where there is long compared to the world. The impact data we feed the data from to the psychometric uh is the S-shaped function. After feeding the data, the value corresponds to 50% considered as the subjective equality PSE, and the gain values correspond to the 25% or 75% considered as the upper and the lower detection that regard after you know, And then Can you hear me?
Yes, yes, we can hear you now.
Yeah, that's good now.
Okay, sorry. So I'm using my mobile phone as the
Okay, that's good.
audio. Okay, so sorry for the delay. So we have to I will firstly go over the work. So we have this is our first work that for the redirected locomotion, and our contributions are the design of the two variable psychometric functions for joint measurements, and we estimate and analyze the horizontal and vertical detection thresholds by conducting a RDJ redirected jumping user study, and we demonstrate the effectiveness of our findings through the game applications. So to do so, we have to divide the jumping into the states. So we divided the jumping to the standing, the ready, the ascending, the descending, and the landing, and the standing states. This can be detected using the head-mounted display and also the tracker and the controllers. So we can easily determine the states the user is currently in. So this is an example of the real and the virtual jumping states manipulated by the vertical and the horizontal gains. So but it was challenging to for the participants to simultaneously pay attention to the horizontal and the vertical manipulations during jumping. So we have two design choices. The first design choice is to let the user jump once and again, and let the user to answer the question 1 and 2 in a sequence. For example, after the jumping, we let the user to answer whether this jumping distance in the virtual space is longer or shorter than that in the real world. And after this answer, we ask the second question, whether the jumping height is higher or lower than that in the real world, and we get the second answer. But we found that the user it was very challenging for the user to remember the two-dimensional jumping states during one jump. So we came to another solution that let the user jump once, and then we asked him the question of whether your jumping distance is longer or shorter than that in the real world, and let the user answer. And then we let him jump again. And then we ask the second question, whether the jumping is higher or lower than the real world. So we get the second answer. So the user have to jump in two times much than the original than the design 1. The design 2 let the user jump more. So this is an example of how the user perform the jumping process. So he is in the virtual scene and jump, and then answer the question and go back to the original position to jump again. And here are the results. So remark that in previous work, the researchers have used the one variable psychometric function to fit the jumping data. But now we have two jumping directions, the horizontal and the vertical. So our function is two variable psychometric function, and we use the previous detection thresholds. For example, the upper detection threshold, the UDT, as the 75% of the data, and the lower detection threshold LDT is 25% of the data. And we have, instead of getting the curve, S-shaped curve, we now have the 3D surface of the fitted data. So if we look from the top view of the surface, we can have some initial conclusions. For example, if you look at the figure on the left-hand side, so if the vertical gain increases,
the imperceptual range of the horizontal gain also increases. And if you look at the middle figure, if the horizontal gain increases and the imperceptual range of the vertical gain also increase. And if we enclose the curves, we can have a area and we can sample gain values within the area that is safe. The user may not perceive it. So we can reduce the required physical tracking space for the VR experience without the user's perception by slightly increasing the vertical gain. And we developed the two applications, the gaming application. So we tested the theory of what we found of the detection threshold of the game. So first, we let the user to play the box jumper game. So we place some boxes in the virtual environments and let the user to jump over the box. So and we ask the user whether the jumping distance in the virtual environment longer or shorter than that in the real world. And in the other application is it's a Super Mario game that we place some boxes in the mid-air and 0.2 higher than the user's head, and let the user to hit the box. And we ask the user whether the jumping height is higher or lower than that in the real world. So this is the user study procedural of the games. Okay, so here are the results of the user experiments. So we use the three groups of the gains. The lower group, we set the horizontal and the vertical gains of both of 0.8, and the upper group we set the horizontal gain as 1.4 and the vertical gain as 2.0. And the control group we set the horizontal and the vertical gain as 1.0. And we have some values of the physical distances. We found that in the upper group, the user jumped shorter than the control group horizontally, and the upper group jumped lower than the control group vertically. And we also found that the lower group, the jumping distance is longer than the control group, and the height of the jumping horizontally is also larger than the control group. So here are the limitations and conclusions. The limitations that we only tested the standard two-leg takeoff jumps, and the measured detection thresholds may not extend the other kinds of jumping actions. And we only explicitly investigate the horizontal and the vertical detection threshold. As a conclusion, that the imperceptible range of the horizontal gain could be affected by the value of the vertical gain and vice versa. And by slightly increasing the vertical gain, we can reduce the required physical tracking space for VR experience without the user's perception. So in the second work, we investigate the virtual physical environment alignment with directed walking. So the problem is, how can the users reach the virtual object while also reach the corresponding real one in the physical space? So this is the problem. And there are some previous work of the passive haptics. There are some Professor Frank Slinicki in 2008 have investigated the taxonomy and implementation of redirection with passive haptics. So the method is to divide the user's working process into two parts. The first part is more general, to use general redirection process such as steering to center problem to let the user walk in the center of the room as more as possible. And the second state is to perform the passive haptic redirection. This is conducted by the taxonomy. And following Stanicki's work, Professor Wang have proposed a constrained path redirection for passive haptics. So here is the example and a demo of the work. So following Professor Wang's work, there's another work called the reactive alignment (REA) from Gerald et al., which is the best paper of the VRST 2020. So he proposed the artificial potential field for this problem that use the pull force and the push force and optimize the forces to let the virtual and the physical points align. So our contribution of this problem is to propose the transferable virtual and physical alignments. So if there are more than one point in the physical space and more than one point in the virtual space, we can allow the target positions can change. For example, we can let the yellow point as TP2 to match the green point TV2, and we also let the TP2 to match TV3. So in this way, we can use the physical space as much as possible to reuse the positions that can be matched to the positions in the virtual space. And we have proposed a reinforcement learning based approach to train the method for the alignment. And we have proposed a novel reward function design, including the dynamic virtual physical target matching and virtual target weighting modules. And we have demonstrated this method using the simulation and user studies. So this is the training pipeline. So we feed in the observations of the user, both in the physical space and the virtual space. We use the orientation and the position as the input, and we use the PPO framework to train the network parameters, and the output are the gains for redirection. And the novel one, the novel part of our reinforcement learning framework is that we have proposed a novel reward that involves the distance term and the orientation term computed from the states of the physical and the virtual space. And we have also evaluated our method with the baseline method and the REA method, the reactive alignment method. That was the best paper in VRST. So the travel is our method. We have evaluated the methods using the simulations with squared environments with different numbers of the target positions, and the physical distance error and reset per pass statistics indicates that our method are better than alternative ones. And we also evaluated the methods in the rectangular virtual environments, the physical environments with placing obstacles, and the different. Sorry, my sharing there's some issue in the screen sharing, and I think I'm offline on my computer. I think my screen is not sharing. Okay, now it works. So yes, we evaluated our method using simulation experiments and also the real user experiments. So as a conclusion, we propose a novel and practical technique for VR scene navigation and interaction, and we achieve better environmental alignment results than the SOTA techniques. So the third work is about the platform of the redirected walking. So we have noticed some problems that there is in the redirected locomotion field, the open source methods were seldom available, and there is no recognized benchmark published for equivalent and qualitative evaluation of the methods. And we noticed that there is a toolkit named IDWT, developed and released in 2016, but it lacks of the multi-user working support, lack of the complex scene support, and the reinforcement learning support and SOTA algorithm implementations. And there are actually a lot of locomotion techniques with different redirection controllers. For example, the subtle ones and the overt ones. There are the classic algorithms that steering to the center, and also the artificial potential fields, and also the deep learning based methods that need to be developed or deployed by the users. So the user have to re-implement their algorithms by themselves. So to deal with this issue, we have developed and released the platform called OpenRTW. So our contributions is to support the multi-user working in shape and size varied tracking spaces. We support learning-based models and passive haptic feedback deployment. And the implementations and the open source of the SOTA RTW methods with unified APIs. And we do the quantitative evaluations across methods based on the OpenRTW library and benchmark. So here is the overview of our OpenRTW library and benchmark. So on the left-hand side is the library. We support the customizable RTW controllers and the simulation and the real walking, and also data logging, and we support for reinforcement learning. And on the right-hand side, we support the different tracking spaces, multiple user walking, and general and real walking passes, and the classic and the SOTA algorithms. So here is the library architecture. So we have the movement component, the path component, the sort algorithms, and global configurations, visualizations, and the analysis modules. So I maybe jump some slides. We can go faster. So I will jump the details of the architecture. Okay. So yep. So in our library, we have implemented a lot of algorithms by ourselves with the unique API. So we implemented classic controllers, the sorter controllers, and the resetting controllers with both the rule-based and also learning-based methods. And we support the very detailed evaluation of the redirected working using different configurations. For example, different size, areas, and different methods and different working passes. And we also support the high quality images and the videos that can be used in your paper, in our paper for the community. And we are happy that several papers have used our platform to implement their paper, their method, and publish their paper. So this is the conclusion of the platform. And then I will introduce the last work, that the room scale environment fusion for efficient traveling between separate virtual environments. So the problem is how to allow the users to frequently travel between scenes, and how to address the dissimilarities in user perception across the distributed environments. So to solve this problem, existing methods allow the users to teleport between scenes. For example, the instant teleportation methods allows the user to walk in the circle and teleport the body to the other virtual room. And the virtual portal technique that allows the user to walk through a virtual door that connect the different rooms. But there are some challenges. Firstly, the occlusion hinders the user perception of ongoing events, and abrupt context changes negatively impact the user's visual connection. There are still a lot of area in front of the user that are blocked by the wall. So we propose the scene fusion technique that we seamlessly fuse the two distributed virtual rooms, and we integrate the distributed room into a larger room by blending and connecting the structure of the walls and blending the textures, so the user can walk directly to the other virtual environment. There is no wall in front of the user. So this is our idea. And we propose the novel design rationale of the environmental fusion technique, considering the efficiency, the virtual plausibility, and the versatility, and enable the users to actively travel between the virtual environments with continuous visual change. And our method with experiments indicates that it outperforms existing techniques on the efficiency, the workload, and the preference. So yes, so the fusion process is illustrated with a video, but I guess it will be maybe not clear due to the network issue. So I will jump it. So we have conducted user studies to evaluate our scene fusion technique with the prop searching and task. The user have to search for the probe from the one room and pick it up, and using one of the three techniques to travel between the virtual environments, and then place the virtual prompt to the targeted position. So this is a trial of the searching and place task. The users have to repeat this task using either of the techniques, the instant teleportation, the virtual portals, and also the scene fusion. And we have conducted the user studies the whole 8 the 10 by 8 and 16 by 16 meters. And the results in this user study indicate that our method, sorted as SF, have the shortest movement distance and the least completion time of the task and the lowest task load of the task. And we also conducted another study that lets the users collaborate Can you see my screen? Yes. Okay. So the second study indicated that our method still have the shortest movement and the least completion time and the lowest task load. So in this work, we facilitate the efficient traveling between the scenes in virtual environments for single user exploration and multiple user collaboration. And we have our method get the lower time cost, the walking distance, and the cognitive load compared to traditional methods. So I think that's all for my talk.